Hi, I'm Alex Hines, a tutor with the School of Computer Science and Engineering, and I'm going to talk to you now about implementing an ADT. Just to recap, in the last video we looked at ADTs, abstract data types, from the user's perspective. This video we're going to think about ADTs from the implementer's perspective in terms of all that potentially complicated stuff that happens under the hood. And I'm going to break it down into a few key sections in terms of how I think about ADTs and how I try and implement them in terms of best practice, I guess. I start by thinking about testing, and I write some general test cases in terms of the expected behaviors of our ADT. So, for example, in a set, if I wanted to add an item, I want to make sure that that item is in the set. So, as long as that behavior is being adhered to, the implementation doesn't matter. So, write the tests with the expected behavior. That allows you to then fiddle with your implementation and make sure it's still consistent all the time. So one set of tests, potentially multiple implementations, it doesn't matter. I'm then going to sort of test out that theory, I suppose, by having a few different implementations, and you'll just see they'll still produce the same behavior even though the code looks very different. And particularly with respect to a set, I'm going to look at, very quickly, I'm going to look at an array-based implementation, a linked list implementation, and a sort of a hybrid linked list hashing implementation. And you don't really need to worry about some of these things. They're going to be sort of complex, but the idea is just to show you that from the implementer's perspective, I can change and swap out things as I so please, but I'll still get, as long as I still get the same behavior and it doesn't really affect our ADT. So what I've said in the previous video is I've talked about the use cases and how we interact with it from an interface point of view. Now, we've created our interface in the previous video, and we've agreed upon what our set needs to do and how we're going to hopefully get some behavior out of it. So we've seen the functionality in our .h file. Now, this .h file is not going to change from this point of view. It could change if we wanted to add further functionality down the road, but we're not going to change any of these functions in terms of name or behavior. We're going to keep them exactly the same. And I'm going to show you how we can implement something in different ways and still get the same behavior. And that is the key principle of ADT. So let's go over here and start by thinking about the behavior that we're trying to get out of our ADT. So what I've done is I've set up a number of little functions which at the end of the day all they do is just run the behavior of our ADT, and they do some really basic use cases. So assert s does not equal null, add s to 12, assert contains s12, etc, etc. And I've got some little print statements here. Now all this sort of stuff is super useful in basically making sure that our ADT is behaving as it should be. If all of these tests pass, if contains S12 works, then we know that our set is working. We could write much more tests and much more extensive in terms of edge cases, but these are just some basic ones looking at unit tests. So test contains, we're going to run some tests on contains. We're going to test add. We're going to look at add, and again, sort of similar use cases and similar testing. I might do some testing with discard, and it's important to run these tests sort of one after each other and think about one, hopefully making unit tests that don't affect the next unit test. So I'm going to make sure that add works because I'm going to use add in discard, and I'm going to use contains in discard too. So make sure that those two tests work, then move on to discard. So let's just quickly write some more quick tests and add them to discard. So I might just copy some of this across. Well, new set, okay, that makes sense. We're going to delete the set as well. And maybe we'll add to discard, well, hang on, we'll add S12. Okay, cool. And at this point, I guess to make sure, I mean, this is not really testing discard, but we might as well put it in there just to make sure it's working. Discard at this point S, and we discard 12. Oops, it should be S. And that should have hopefully discarded 12. I mean, the simplest way, I suppose, to test that would be assert S contains, but as opposed to that, we'd actually want does not equal, well, equals 0, which is the falsy case, if you like. Okay, cool. So we'll just leave that there for now. I don't really want to labor discard, but again, we could do a similar thing for size, and I'm just going to do some really basic tests to add on top of that. Add S equals 12 contains, and I'll just assert that size S equals 1. Okay, cool. And I've just got this final test, which basically just prints out the whole set, just so you can see what's going on, but maybe I'll make it a bit smaller. Maybe I'll make it a size of 20. Okay, cool. So that is all the stuff in terms of testing. Now, you might think, oh, this seems a bit arbitrary, that we're just adding all these test cases. Actually, quite the opposite, because all of these tests should work on no matter how we implement. And I'm going to show you some implementations in a second, but the nice thing about creating this test file, which is going to run all our tests, is we can make sure that the sets that we're making perform as they should. I keep saying this again and again, but consistent behavior is the whole point. Okay, so discard, I had a little bug, but I've fixed that now. So we've got all these functions which are working in the principle of essentially a linked list. This is really a glorified linked list implementation, and it does most of the things a linked list does. It also has some little helper functions here, like this is actually just legitimately straight from a linked list add node, and we also have a few other ones which are really not related to the set implementation at all. Cool. So the idea of showing sort of this sort of stuff is not for you to sort of see what is going on here, but it's more just to see that this is one way which is producing the behavior that we want it to. So again, on this terminal side, there's not a we're getting all the behavior that we want out of our test program. So this is a valid way to do it, and we could do it many other ways. I'm going to make real use of our test case now, because I'm going to show you another example, and this one is a bit more, well, it's just very different. It's similar in some respects, but quite different. Okay, so this implementation is quite different again, and we're using sort of a hashing system. As I said in the last thing, previous one was very much linked list. This is kind of like a linked list merged into a hash, but it's a very different looking ADT in terms of the implementation. So we've got some helper functions which are here. These are all related to the actual ADT, but the user doesn't see them. We still have all of our normal functions. So we've got new set, delete set, size, add, append, discard, contains, print set, redistribute keys is a helper function. We've got some other intersection down here we haven't even made yet. So the idea here is that we're giving the same behavior, and we can prove that by just compiling the same program with the same main, and that's as our test file. And again, we get all tests passed, which means it's passed all of our behaviors that we've wanted. So cool, that means that this whole implementation using a totally different method is still passing our tests. And the key here is that from the user point of view, behavior is the same, but the implementer has totally changed the way they've made it. And just finally, another valid way to do this would be to look at something like implementing using an array type system. So you would do something like a malloc, the size of the struct to start with, and then just initialize the variables, initialize the array. And in this case, I've actually just used that we're using positive integers up to 32,000, which is not necessarily strictly true, but it will be a positive integer. And we're initializing our array. Now I'll just quickly add a few of these just so we can show that it is working. If we just do free s-lms, and we also do free s, that will sufficiently delete our set. Okay, int size. This one is pretty basic. This one will still work in our case, which we did before, which is just return s-num elements. So this, I mean, some of these functions are going to be exactly the same, but they don't have to be. What else are we going to have? We're going to add. We would just, and this is going to be not the most ideal, but just to show you how it would potentially work, we would do something like s-lms, and then we would do the index associated with the int, which would be n equals 1, and that would be to show that it is in the set. And again, this is not the most ideal way to do these things, but discard s-lms n equals 0. Cool. And that would work even if the element wasn't in there. So this is very basic implementation of a set. Contains, simply return s-lms, and we would do something like s-lms equals 1. So if true, then true. Cool. And finally, oh well, we will just leave the print set implementation, but this is a very simple implementation. It would easily be broken, but the idea is really just to show you a totally different way of making exactly the same thing happen. So I'm just going to save that, and I'm going to recompile one final time just to show you this final example. And this is called a set array, and that compiles. And well, there we go. Good example of what to do when you are changing things around. Very obvious fix, which I'll just amend now, and that is s-num elements plus, and well, this is assuming that if we added something, and that's fine. Let's just pretend that this is the this may cause issues, but let's just see if we can make our tests work with this. Not quite. It's not letting me do that. But the idea is, this is because we're not changing. The idea is really that we can change the implementation and not affect the end product. I'm going to put all this code up online so you guys can have a look and play around with it at your leisure. But yeah, this has just been to expose you to the setting up tests, which give grant behavior, then building and creating your ADT, which delivers that behavior. So that's pretty much this whole video, and you'll if you want to see more of the code, as I said, it'll be all online. All right, so that was an idea of how we can change our implementation of sets and still have the same behavior. Again, I'm going to put all this code up for you to look at your own pleasure, and I've put plenty of comments in there to make it a lot easier. You can play around with maybe make your own set as long as it passes those tests. All right, thanks very much.